So welcome viewers to Beyond Phrenology. Happy Monday to everyone. We are back at Beyond Phrenology after a long time. I took a several months break while I was working on more involved in research projects and grand deadlines, and we'll talk about why that's the case with Andrew today. We are delighted to have with us today Andrew Maurer. He's an associate professor of neuroscience at University of Florida. He does really cool work on hippocampus. We'll go into a lot more details with Andrew, but the discussion today would be very general. We'll talk a lot about neuroscience, what we think about the brain, how the general neuroscience community thinks about the brain, how it directs our research, what are the paradigms which challenge these current notions of which are dominant in neuroscience, and a lot of related ideas about career, psychology, neuroscience, life as a scientist, and things like that. So, Andrew, welcome to Beyond Phrenology, and I'm very
Hey,
excited
thanks for having me. Yeah, I'm excited to
Yeah.
talk to you too.
Yeah. So, Andrew, I gave a very brief introduction about your work. When I read your work, definitely you're interested in hippocampus, and a general audience feels that hippocampus has a lot to do about memory and memory-related tasks, but I think it is much more nuanced than that. So let's start with a little bit about hippocampus, as well as then we would like to know how you end up doing what you are doing currently.
Yeah, it's a really unique question because I started out in my career in the hippocampus began with my graduate work with Bruce McNaughton, and we studied hippocampal place cells. And are you familiar with like place cells are these neurons in the hippocampus, and if a rat's wandering through an environment, one of the pyramidal cells might fire in one specific location. And then there may be another cell as the animal moves off into another location. It's different. That's one cell stops firing and another cell picks up. And the phenomena is so robust that people have began to think about these neurons as the spatial map or the neural mechanism of path integration in the brain. And so that's really where I began and cut my teeth on hippocampal physiology and thinking about it from a spatial navigation perspective. Of course, along the way, all the research stemming from Scoville and Milner and their research with HM, there's a whole entire literature base linking the hippocampus with memory, and importantly, episodic memory.
Yeah.
And undeniably, lesions of the hippocampus create exacerbable, it's demolishing the amount of impairments that these patients have in terms of generating new memories or holding on to new memories. However, in my postdoc, I wasn't necessarily enamored with the pure memory or the pure spatial navigation theories. And I kind of started drifting away from them. And I think it was something along the lines that I read from Donald Hebb. In his textbook of psychology, he writes that it's a mistake to think that the process of vision resides in the visual cortex. And in the same vein, it's a mistake to think that the process of memory resides entirely within the hippocampus. And he starts arguing for a very distributed way in which the brain interactions across many regions are important for visual imagery or memory or decision making. So I kind of started drifting away from the limiting perspective in my viewpoint. The limiting perspective is saying the hippocampus is purely memory or purely navigation. And I assure you that the hippocampus is engaged in like artistic expression or construction of music.
So this directly speaks to the theme of the podcast, right? Like Beyond Phrenology, I have the phrenological map, behind me, and a lot of modern work is kind of, a new age phrenology in some ways, right? When we try to localize brain areas extremely specifically for a particular function, which we are able to test mostly using fMRI in the lab, right? Um, so where do you think we are with, like, for instance, with hippocampus, when you say that, yes, it is involved in other things, right? And like to my grandmother, it will be fairly obvious because she'll say, yeah, your kidneys are also involved in thinking, because if you don't have both kidneys or like at least one, you're not alive, and that's why you're not able to think. So when you say that it's more distributed than that, how do you define the distribution? Like, does it also involve kidneys, or it involves still only other parts of the brain because
That's a great question.
right?
Yeah, there's an old anecdote. It was written by Case Vanderwolf, who was one of the big. He was a proponent of hippocampal physiologies in the 70s, and he's credited with his a lot of basic research in terms of the hippocampal theta rhythm. But in one of his books, he talks about the curious case of Professor Omega. And
Okay.
Professor Omega has an experiment where it's very much set up like Pavlov's dogs, where he has a dog and the bell rings and the dog salivates. And so he's thinking to himself, like, it's not, I don't think all of this is purely in the brain. I actually think some of this is embodied in and we can find neural signatures of memory elsewhere. And so he records from the pectoral muscle of the dog.
Yeah,
And so the bell rings and the dog sits up straight. And then, of course, the pectoral muscles engage. And
of course.
he's like, he tells everybody, like, this muscle anticipates the food delivery to the point that we can actually say that this is indeed related to memory. And the story goes on that he submits his paper for publication for Professor Omega, and he gets rejection after rejection after rejection. And he says, I don't understand why I'm getting rejections because I'm using the same logic that all the neuroscientists are.
Right.
And then I'm just showing that there's a correlation. And he's like, if I lesion the pectoral muscle, the dog doesn't get the food. So obviously there's and so there is this sort of question about where can we start to drawing the boundaries between what we consider cognitive processes and the body. And I think that this ends up being a challenging question should anybody start considering the nervous system an open system. And what I mean by that is it's never purely contained within itself, and there can always be something external in the environment that will help me remember something in the past. And it doesn't need to all be initiated in my brain. I could have a pain in my back and have it like, oh, I remember that time that I was playing football in my
Yeah.
backyard. And so it's an external reminder. But I could also go to sleep at night and have a dream about when I was a kid playing football in my backyard and then remember the event through that pathway as well.
Yes.
So
So remembering, yeah, the pain, in the memory.
Mhm.
Yeah.
Yeah, and so it's funny because you bring up the kidneys, and I guess I would never say that kidneys are involved in memory, but it's very much taking a more holistic approach. My car needs a whole bunch of things to drive and to accelerate. And
Yeah.
so if I take out the carburetor helps make the car go. If I take out the gas pedal, the car makes the car go. If I take out the brakes, I guess I'm okay
Yeah.
because my car will still go, it just won't stop. So there's always a whole bunch of different ways that we can make the holistic totality of the organism fail. And we should try to be careful in determining what's necessary and sufficient.
Right. So that brings down to, how exactly do we interpret the role of the brain? So for instance, in the case of, Dr. Omega, right, the experiment. So it's a completely similar logic, which is leading to a false conclusion, or it's like intuitively a false conclusion, right? So do you think we have something missing in how we do neuroscience right now, which dissociate us from, or we from what should be the insight about how the brain functions or how the central nervous system functions? Even that is a question. Are we trying to understand the brain as like the mush of fats, carbs, and proteins inside the skull? Or are we trying to understand the central nervous system? Or are we trying to understand how it both together interact with the world? Like, what exactly are we trying to understand? Like, do we have, as neuroscientists, a clear idea?
That's a great question. I can I ask you what do you think first? Like, do you think that neuroscientists are studying the appropriate thing in order to make advancements in terms of I guess at least what was initially defined in the Brain Initiative and
Yeah.
start improving outcomes?
See, I have two, immediately reflex responses to that. One at the domain of what I do, and one in the domain of, how I came to do what I'm doing. So for instance, right now I'm trying to dissociate myself a lot more from theoretical, assumptions about the brain or about the body in general. And that's why you'll see, even though I call myself a neuroscientist or I wanted to be a neuroscientist, I'm going more and more towards statistical physics and analyzing behavior from statistical physics standpoint, because I don't need to assume anything about the brain. I'm just talking about the data and patterns in data. Okay, and that void was created because I was very passionate about psychology and neuroscience, and the more and more I read about it, the more and more I felt like a lot of it was house of cards and assumptions and theories which were untested. So I personally think that a lot of neuroscience have gone astray from it. It doesn't even know what exactly it is trying to achieve. And we have got engrossed in a culture where we are methodically and technically very proficient with more and more instrumentation and more analytical methods. But we do not have, like, I won't say any idea, but in a lot of cases, very little idea of what we are trying to achieve. Because I mean, when we are able to do something in physics and other fields, we have a predictive capacity. So for instance, if we understand a system, we are able to predict how under certain conditions the system will behave.
Mm-hmm.
When it comes to the brain or central nervous system, when it comes to physiology, we know a lot more. Like in terms of neurophysiology, yeah, we have really solid understanding of how the system functions, under certain constrained conditions. Or when it comes to the brain and what exactly it is doing, what are the parameters it is trying to control or not, I don't think we have any predictive capacity. Uh, like if there are papers on fMRI, for instance, that these kind of people have this kind of activation, but we do not have any predictive capacity. Like if I tell you, like, this is the person, can you predict activation patterns based on that?
Yeah.
So what exactly are we trying to do if you do not
But
have the predictive capacity?
I love this. So in my office on I close my door, I have pictures of two people on my door, and one of them is Ludwig Boltzmann. And Boltzmann is the father of statistical
Yeah.
mechanics, and
Yes.
he re-derived the second law of thermodynamics, I think, through a statistical mechanics approach, and he was ostracized for it.
Yeah.
He was derided. The poor guy, he incredibly brilliant, lives his life like working through the statistical mechanics approach, coming from a thermodynamic perspective, and he never sees the fruition that his perspective brought. And it's one of these guys that his brilliance ends up being his burden. And so I remember thinking about Ludwig Boltzmann, and I remember thinking about my own dissertation research where we're giving high importance to individual neurons. And it was through conversations with one of my great collaborators, Alex Shermat, in which we started discussing that the individual state of any neuron is perhaps inconsequential. It's not a single neuron is not going to give us the keys or the insights that we need
But
as neurons.
but I have heard that there are neurons which can code for like Angelina Jolie and Brad Pitt,
Yeah.
the grandmother neurons.
Well, so this brings us to the second point that you were discussing, and you use a really interesting phrase, "house of cards," right? In which the Brad Pitt and the Jennifer Aniston neurons were always like the reconceived idea of the grandmother neuron, the
Yeah.
Gnostic neuron. Like,
Right.
and if you got rid of this single neuron, you get rid of all your memories of your grandmother, or you get rid of all memories of Jennifer Aniston.
I think we have movies made on that concept then,
Yeah,
right? Yeah.
exactly. And it's funny because, and you brought up another point, you said encode, and it's when a neuroscientist says encode, more often than not what they really mean is correlate.
Exactly. I mean, encode or represent as well.
Yeah, and it's funny because it's the weakness of the neuroscientist's own verbiage that locks them into the models that they use and the manner in which that they view and interpret their own data.
Yeah.
And so if you're very much believing that there must be a way for the visual cortex to represent faces, then you're only going to seek there's a danger in which your hypothesis ends up being your biggest weakness, because nobody wants their hypothesis to be incorrect, and
Right.
so they seek to affirm it.
Right.
But in all actuality, the best scientists, and the only way we can really approach science altogether, is by trying to disprove hypotheses.
Exactly. I mean, I was trained in a Popperian method, and one of the most influential articles which I was given as an undergrad was, Strong Inference by Platt, published in Science, And the article talks about like how molecular biology, for instance, I mean, we now know the caveats in molecular biology as well, especially when it comes to machine metaphors. But it had a lot of progress at some point because of strong inference. But when you actually talk about neuroscience, for instance, very rarely you see something or an experimental design to refute something. I mean, they're refuting, but they're refuting at the level of null hypothesis, which is a statistical kind of child's play rather than actual science.
I man, I 100% agree with that. If you look at any statistics paper to come out in the past 30 years, I think you'll see, especially with the big papers, you'll see it's rare to see a paper with fewer than 30 authors, especially
Yep.
in theoretical physics, because the silos have broken down and everybody understands that the big problems are best tackled by big teams,
It seems, yeah.
interdisciplinary teams. And then the other one is they don't, the physicists are not handcuffed, nor do they feel like they need the blessing of statistics.
Yeah.
Because, and neuroscience is still a field that very much requires the internal uh, encouragement that a p less than 0.05 gives them.
Right.
And usually, more often than not, this begins, at least a more cynical aspect of myself makes me think that we're likely to find statistical significance in phenomena that are actually not biologically significant at all.
So that brings down to like literally whenever, so I almost accept every review invitation these days, just because to keep myself occupied. So, so you wonder sometimes, so many articles report like p-value without even talking. I mean, even if they have the effect size, what does it mean biologically? Does it
Mhm.
even matter? Like, yeah, you see this change in, for example, an elbow flexion, like, yes, 3 degrees change after this intervention. What does it have to do with anything related to behavior or well-being or any consequences for what the whole field is for,
Mhm.
right?
Yeah, it leaves us in a different. It's a difficult perspective. I don't know. Like right now, the hot debate in my field is whether or not we use frequentist distributions or move
Yes.
to Bayesian
Right.
statistics. Uh, I still worry that it ends up requiring a lot of external collaborators and statisticians to come in and look at the data. I still get upset when I see everybody running parametric statistics on what we know to be a non-parametric distribution.
Yes.
I I I hope that eventually what we start working towards is a very open data movement where it's actually the data can stand by itself, and we, with the data being freely available, the requirement to describe the distributions in statistics should start to become sidelined.
But these are still, very kind of I would say tactical level, things. Of course we are improving in general on those and we'll keep on improving. But still, if we are working in the same umbrella of assumptions, then no matter how good the stats is, or no matter how good the open source,
Yeah.
movement is, we will still be working on with the same, wrong or erroneous or limited assumptions, howsoever somebody might put it. So where do you think in terms of the overarching theme? I mean, for instance, the Brain Initiative this year, the budget for Brain Initiative has been drastically cut down. Okay, for starting from 2024, I think by 40% or something. So the dissatisfaction about neuroscience and in general what we have gained more about the brain is kind of brewing in some ways because we started with a lot of big promises, the European Brain Project as well as the US Brain Project, you know, and there were false promises that we'll be able to completely map the brain, delete memories and things like that. So, so where are we getting there, in terms of uh, making it actually delivering on the promises or reshaping the promises so that they are in reality?
I mean, you hit the nail on the head. I really think it comes down to every experiment begins with a premise or an assumption. And if that assumption eventually proves invalid, or the premise proves invalid, then everything that comes after in the paper is most likely varying degrees of incorrect, right? And I do worry that a lot of our initial experiments or that are conducted in the laboratory come under the assumption that William James wrote about attention and objects and spatial memory at the turn of the 1800s and the 1900s in his book.
Right.
And Yuri Buzaki has a nice paper in eNeuro where and I think this was also a chapter in his recent book, in which he discusses how there's a limited utility in still conducting neuroscience under the assumptions that these processes actually have biophysical manifestations within the brain and that they actually evolved as such.
Right.
And so to kind of pivot, when I think about memory, I think about it from I can try to think about it from an evolutionary perspective. And I have to start asking myself, memory has to exist in an animal prior to where there would be a neuroanatomical region that everybody would agree on. That's the hippocampus.
Right.
And
Exactly.
and, and so we end up playing this game. Does a
Yeah.
C. elegans with 302 neurons have memory?
Yeah, so it has to be evolutionary tractable. You cannot have suddenly an evolutionary punctuation that, yeah, here is something, like a new DDR4 RAM suddenly coming out. It has to be, again, sorry for the machine metaphor, but easy to understand that way.
Yeah,
You have to have an evolutionary trace.
absolutely. And so I that was one of the things that kind of pushed me away from talking about memory and into broader concepts such as stimulus equivalence, or how we how you woke up this morning, you got out of bed, you ate breakfast, you did all these things, and your consciousness never collapsed.
Yeah,
You were able to maintain what we call the train of consciousness. And I always think, well, that's a fascinating neuroscience problem in itself. Who's studying this? How do we maintain our flow of consciousness? How do we maintain our cognitive continuity from when we wake up in the morning all the way to when we go to sleep? But I
right.
also think and so it involves that sort of thinking involves dropping a lot of the assumptions that we exist in our textbooks and starting to ask broader, more philosophical questions. And you also touch on that it's not so vogue right now to be a philosopher when you could publish in boutique journals with great feats of technological strength.
Right.
So if you have a triple transgenic mouse and you can shine one laser and turn neurons off and another one to short time them on in the same animal, you're almost guaranteed to publish it in a high tier journal, even if the premise is not necessarily as strong as it should be or holding up to the rigor that existed 40 years ago. If
Right.
I tried to publish in a journal and said I injected a virus in the rat's brain, but don't worry about that, everybody. This
Yeah.
is the ephas data I got. I'm sure I would have some reviewers like, no, you have to tell us about how much inflammation was caused. You have to prove that glia weren't activated. But I think AAV is the tool of the trade right now, and I think it kind of does leave one to wonder if we're kind of in the dark era of neuroscience. Like this is the bloodletting where we
Mm.
know something, we know enough to be dangerous, but we don't know enough to actually have great answers for the big problems.
It's very interesting. So I was at a cafe called Andala Cafe in Boston. So I used to live almost like in the center of, from when you go from MIT to Harvard. So I was at this cafe and there were like three graduate students from MIT. And we started discussing, like shared interest. And then something happened and I told them like sound is not a signal.
Hmm.
So the idea was that, yes, once you have a condenser mic or something, where you're recording, you're taking the impressions of sound waves and then, you're converting into electrical signal. Yes, it's a signal. But sound in specific in itself is not a signal. Okay. It's like a physical flow of something. Okay. So you cannot think of, everything as signals, because when we come up with a signal processing approach, and just because we have these things which can measure in electrical, random, like whatever fun sampling method, and you have these electrical magnitudes based on some instrument, that doesn't make what you measure as signal, right? Our processing techniques are signal processing techniques, but what we are studying is basically a mush of something getting converted into another mush of something. The guy almost was ready to punch me because it was such an kind of a dangerous, or you can say intimidating an idea, for when you think everything from the signal processing perspective. So this is another thing which I wanted to ask you. What do you think as neuroscientists? So I feel that because we invented electricity and we could invent probes to put inside the brain and record electrical activity from the neurons, and because we could see those spikes, we actually have kind of got conditioned now to think everything in terms of the spikes and spikes carrying that information as signals, completely forgetting that it's like a chemical mush and spikes might be an epiphenomena of
Mhm.
a kind of a discrete space in which those chemical activities takes place.
I think you find yourself in good company when you start thinking about action potentials as epiphenomenon, because I think Earl Miller at MIT
Yeah,
also has a similar perspective that spikes are the epiphenomenon in all of this. And of course, like the the electrode is a tool of the trade of the physiologist, and when all you have is a hammer, the world looks like a nail. And
right,
so it ends up with this perspective that there's a tantamount importance placed on the action potentials when it's actually the communication between neurons is truly chemical to chemical.
right.
Other, of course, there's always exceptions in the nervous system. There are gap junctions. They do share a common milieu where there may be ion flux and subjected to the bipolar aspects. But I would agree with you. And then I think one thing that most neuroscientists may not fully appreciate is even in the best monosynaptic connected conditions, the presynaptic neuron will fire an action potential. The action potential will flow down the axon. It'll come to that postsynaptic neuron. About 10% of the time is the maximum efficiency. 10% of the time, the
Okay.
postsynaptic neuron, and the other 90%, it doesn't. And so the action potential fails to elicit another action potential 90% of the time.
Oh, so in that sense, that if you're talking about the population of neurons and you're talking about that population of neurons acting together, you cannot ever find like a consistent activity level, because the more the number of neurons, the combinations in which you can find any consistent, flow would be like statistically improbable.
Yeah, I don't know if it's given it. So I'm actually talking a very specific condition where it'd be a pyramidal cell in CA1 and it has an axon and the axon projects to a local interneuron.
Okay.
So so if you record thousands and thousands of action potentials from the presynaptic pyramidal neuron,
Yeah.
it will reliably create an exponential in the postsynaptic neuron at a latency of about 1 to 5 milliseconds,
Yeah.
but that's only about 10% of the time.
So there are two factors here. First, you have a variable latency, and second, you have a variable probability,
Yeah.
right? And that's just at the level of monosynaptic connection. And
Hmm.
when you have more and more neurons, like that communicating, then you have latency at each synapse as well as the probability at each synapse. So we're talking about an ensemble, and that whole improbability as well as all those delays at different levels, creating a consistent behavior or consistent flow of activity at another level, right? So
Yeah.
do we understand how that translates? I mean, because when we say when it encodes information, are we saying that, yeah, of course it has to encode, or like it has to behave, but do we have the adhesive to fill these gaps in terms of our understanding?
I think this is stuff that I think you and Damien think about a lot. Damien Kelty Stevens,
Yeah.
Dr. In which so but I and so I'll give my answer, and then I hope to hear your perspective.
Yeah.
I kind of started thinking about things on different scales.
Yeah.
And when we start thinking about a neuron by itself is a very complicated entity with many ion channels.
Yes.
And even the manner in which it can express ion channels in different concentrations relative to each other can give it either can give it very unique biophysical properties.
As well as that, those distribution of ion channels and things like that also change over time.
Yeah, right.
You know.
And it's funny because it can change, and so the physiology changes, and it changes some more, and the physiology changes, and it changes some more, and all of a sudden it wraps back around, and it resembles what it's. So there's
Yeah.
degeneracy in the pattern of ion channel expression in terms of the physiology.
Right.
And but if I knew a single snapshot of everything that that neuron does by itself, and I knew all the ion expression channels, and I knew its IV curves, and I knew how it would respond under different neuromodulators,
Hmm.
a magic problem appears when I put two of those neurons and I connect them together, in which the whole becomes greater than the sum of the parts, and
Yeah.
I can no longer take the rules that I figured out on one level and make a
Right.
linear connection the level above.
And that's just two neurons, and we are talking about
I,
billions.
and so yeah, and then you go
Yeah.
up a level and you're talking about a small network, and you're like, wow, I can still see the action potentials, but I'm not sure if the action potentials are the best descriptor of this network. And then we go to the brain, and the brain has,
Huh.
and we're looking at one region talking to another region. You're like, I don't know. Like the rules I learned about the hippocampus may not be the specific things that I need to apply with thinking about the communication across the entire brain.
Right.
And so I think about this a lot, and I'm curious what you guys think. It falls in the domain of like nonlinear self-organized systems and emergent phenomenon, and how the rules kind of really
Yeah.
the rules are dictated by the interaction of the individuals in the population, and those individuals themselves are kind of ignorant of the rules.
Right.
It's a self-governed population, and they don't actually know what the rules are, but they just obey.
Right.
And so I think about a lot about how we can transfer our ideas from one level to another, just adjacent, let alone from going the single neuron to the behavior. Like
Right. Right.
that gap is so unfathomable to me that I don't even know how we
See,
begin to unravel.
so I teach biomechanics. So I ask my students, like, where exactly do you think is force generated when we actually apply a force? Is it the muscle? Is it like muscle fiber? Is it like the ATP molecule? Like, do you attribute it to the actin myosin? The movement between them, where exactly is the origin of force, right? It's hard to say, because, if even if you have a reflex, your muscle movement have to be there, but your actin myosin filament molecules have to move. So
Mm-hmm.
that information it's not just a 30 millisecond reflex. Within that 30 millisecond, those actin myosin molecules also need to get the information to move and should start moving, right?
Mm-hmm.
So, and that's like cross-scale interactions happening,
Yeah.
back and forth, both in terms of the information as well as in terms of, the effect. Uh, it's hard to say. I mean, I don't think
Yeah.
we're at a level to say anything.
And I'm not sure how I don't teach this in my classes, and it was never taught to me explicitly as an undergraduate or a grad student. But we never. I feel personally I need to expose my students more to the idea that reductionist biology approaches are not the correct way to go about it, because we can't keep reducing the system to smaller and smaller components, hoping to find the insight that's key to
Yeah.
solve everything up.
I think it had its value, and it might still have its value, and even less than it had before. But I think we are hitting a wall, like, very, very fast.
Mm-hmm. And then you think about things that fall in the domain of statistical mechanics, like multi-body planetary motion or
Yeah,
meteorological systems. They gave up a long time ago trying to derive linear causal explanations.
exactly. But we have not. So for instance, when I wanted to ask you, when we say that, brain encodes this information, do we have an idea that what exactly is something that the brain or central nervous system will not be able to encode, right? For instance. So
And No, keep going. I want to hear more about like this analogy. It's like the device that the brain
So
couldn't encode.
it's like this is for everything, right? For instance, biomarker. Everything is a biomarker suddenly because just you can measure using some IMU or some sensor, right? So every data is now has now become a biomarker in like layman language or
Eh,
kind of to publish papers. Now the
yeah.
question is like, what exactly is not a biomarker, right? Where do you define the boundary? And FDA has to put like a special panel a few years back to provide a definition. See, this biomarker has to have some biological basis. It has to talk about a disease, has to be validated. Not anything you measure is suddenly a biomarker. Likewise, when we say that brain can encode something, we need to know where the boundaries of that encoding are, because if we do not know, then we do not, that means that we do not understand what exactly encoding means. So, for instance, if it's just a correlation, like I move my hand, you record from my neurons, you find a correlation between the two, which is also not a linear correlation. You basically do some machine learning to fit a model, right? So there's some kind of play there. And then you call it encoding, which is what normally neuroscientists call, right? We call that brain is encoding that, or those neural trajectories are encoding, in, my hand velocity, for instance. Then the question is that can it not encode my acceleration or like jerk or something, right? As soon as you define a parameter which the brain encodes, you suddenly define a parameter which the brain cannot encode, for instance, right? You're basically restricting that encoding to a particular scale, right? Unless the two properties are related. That's first thing. The second thing is that if you are saying that this correlation is actually encoding, so does it mean that if they are not correlated, that means that that won't be encoding? Is the converse true?
I, so yeah, so I guess like you'll find me sympathetic to your argument in which neuroscientists overuse the word encoding, and they very much always I give them grace. They really mean correlation,
Yeah,
and so in your analogy, so you're recording from the motor cortex, you move your hand and you see a pattern of activity.
yeah,
I would wager that if you had a golf club or a tennis racket in your hand, you might see a different population or activity. And
exactly.
it
I mean, that we already know, right? Yeah,
Yeah, right. And
yeah,
it's the failure of the experiment to not explore broader parameter spaces in order to break out from a very narrow hypothesis driven viewpoint,
mhm.
and rather try to understand it. I think we'd be better off understanding how the brain, how the dynamics of the system are used in a manner by which the brain can organize its own emergent patterns. Eh, And the other one that you mentioned is the machine vector decoding algorithms that are very like you'll put something in there and you'll decode it. I always wondered, like, I could give my son an Xbox controller. He played PlayStation his whole life. I give him an Xbox controller, let him play a game for about 30 minutes, and he's using it like as if it's second nature.
Exactly. Yeah.
That I worry that a lot of our decoding efforts, we're not, especially when it's sort of like the monkey moves the robot arm. It's not so much that we decoded the brain, it's that the brain decoded the device. The,
Which is where they are actually heading now. For instance, BCI people are now talking about like two-way interactions or like
yeah,
BCI based learning, for instance. I mean, people are recognizing this caveat in the designs. Yeah.
no, that's unique. That's really exciting to me because that actually means that they're going to actually let the brain start actually dealing with it as if it's a controller.
So Nico, for instance, Nico heads up all this at Chicago.
Yeah.
So he had some really nice experiment where like amputated monkeys, learned to use basically a handheld controller, and they looked at the changes in activity patterns. And what you see is that over time, the monkey learns, and you see some kind of pruning happening, and based on that pruning, kind of new network forming. So, which is fine, within that scope. But again, it raises more questions that it answers, which is, if pruning is happening and this is the monkey learning, so when exactly the encoding stops and when the learning happens, or is learning itself is encoding? I mean, you see what I mean? Like, what exactly is constant and what exactly is changing, and in what space?
It's almost like the weakness of the argument is looking for the boundaries of when encoding starts or stops,
Yeah,
or when learning starts and stops. Where I
right.
always I joke to my grad students, I'm both recalling and retrieving right now. I'm encoding, recalling, and so I'm
Right.
doing all three right now. And so I kind of find a limited utility in trying to break up neurophysiological processes into these clean, psychologically defined boxes.
Right. Right.
And I often in my class, I'll liken the movement of brain activity through the brain as the velocity of a red blood cell and its journey through the cardiovascular system,
Mm.
and in which it's subject to it's subject to the big macro scale interactions such as the heartbeat. So you'll have the big QRS wave. And then, but it's also subject to friction between other red blood cells and the size of the capillary it's in. So you
Right.
might have really high frequency jitter. It's undergoing all of these all together all at once. And I think with when it comes to the brain, prior to trying to come up with clean definitions of this neuron correlates to working memory, we'd be better suited to start thinking about how at least energy moves across scales, how energy is moved from, say, the visual cortex through the medial temporal lobe and the hippocampus, and then maybe jumping down a scale and saying, how is that energy locally distributed within the microcircuit of the hippocampus? And I think all of that's, we need to understand all of that prior to making these leaps towards encoding,
Yeah.
movement,
Right.
very pre-described, almost self-fulfilling prophecies of experiments.
Right. And I think this is what we are learning from these AI models, because when you look at LLMs, for instance, right, multiple elements, LLMs can produce similar kind of output, right, with
Mm-hmm.
completely different architectures, with completely
Mm-hmm.
different, neural densities or interactions, and multiple, different parameters even, right? So I think, and there's actually a lot of movement going towards like, oh, in that case, like maybe the brain works like an LLM. And instead of that, I think we can take that lesson that probably the properties inside do not matter as much as a more higher scale structure, which comes out of the geometry matters to produce a certain counter output. Because ultimately we are an output producing, objects.
Yeah, I think it's right. I took a lot of my inspiration in terms of how I think about the networks of the brain from Gerald Edelman.
Hmm.
He wrote a book on neural Darwinism,
Yes. Yeah.
and he really, I think he comes at it from an evolutionary perspective, but perhaps tantamount to that, he comes at it from a developmental perspective. And in his book, he discusses the challenges of so a lot of neuroscientists want to wire up the brain as if it was a computer where one single neuron has to send a very specific projection to a very specific neuron in the visual cortex. And then that has to move down the visual cortical chain as we start making more and more complex representations. Gerald Edelman's like, we don't wait, we don't need to do that. In
Yeah.
fact, we just need to get close. We need that neuron in the thalamus to project somewhere in the visual cortex and find a lot of good partners. And then after we have a big recurrent architecture set up in the brain where there's a common dialogue and we can keep propagating activity, we can actually start engaging some of the synaptic pruning to kind of let the connections suss themselves out. And he was almost describing a way in which the brain becomes its own sort of teacher, or the brain is actually a device that can govern and self-organize itself in such a way that it can carve out what the absolute precision is no longer necessary, and very general wiring is sufficient to
Yeah.
begin the process. But you're right, like in essence, I have a neuron in my thalamus that's wired up very differently to my cortex than the same neuron of your thalamus.
Right.
And going back to the brain initiative, it's kind of was the connectome was a big part of this.
Yeah. Right.
That if we understood the connectome, perhaps we'd understand the brain.
Yeah.
And there's a beautiful quip to this offered by Ev Martyr, in which she said that it's absolutely necessary and completely insufficient in order to understand how the neural dynamics of the brain work.
Right.
It's like having a static map, a static roadmap of your hometown. It's really good to show you how you can get to certain places, but it's kind of really bad at telling you where the traffic jams are going to occur.
That's true as
And so
well.
and so I kind of feel like half of the connectome, it was both necessary, but if you come at it from a perspective of thinking about nonlinear dynamics, you really want to know about how the activity is going to propagate, flow, and become distributed.
And maybe there is something. I mean, so nonlinear also, it's kind of it's very dicey to say nonlinear because a lot of times, sometimes the same people with linear assumptions, when you talk nonlinear, they feel that a polynomial is actually nonlinear because it has a
What
nonlinear, like a quadratic or cubic term. When I or Damien talk about nonlinear, we are specifically talking about multiplicative interactions, which lead to long-range correlations or non-Gaussian behavior, right? That's the current understanding. As well as maybe there's something more than nonlinear, which we have not discovered yet. We think that nonlinear is state of the art. Maybe there's something more, right? Because even non-Gaussianity and long-range correlations and variation in those two seem to be not a sufficient amount of variability to be able to account for like everything,
I
possibly.
so I would be curious to hear what you think of this. So when I say nonlinear, I imagine, of course, I go to highly sensitive to initial conditions.
Yeah,
And for me, this is like the if you had 100 neurons and those 100 neurons were randomly wired to each other, inevitably some synapses are going to be stronger than others. And the if that network had zero activity going on and you dump activity into it, the initial conditions are sort of set by the synapses. However, now when we talk about synaptic failure rate and how the synaptic failure rate might change and be awkwardly distributed in the network, if we change the input enough, if we linearly change that input, we might actually. So step one, you have a fixed input, you get an output. You change it a little, you get a little bit of change in the network. You change it a little, you get a little bit of change in the network. You change it a little again, you get a very dramatic shift in the
right,
network
right.
behavior.
Yeah.
So I almost envision a chaotic attractor of sorts,
See,
in
so
which
this, yeah,
we can the brain will always be able to come close and re-achieve the same sort of population vector that it had a time series before,
yeah.
but never is it always absolutely the same as it was.
So you're right on the second part. The first part, uh, when you talk about like nonlinear response, for instance, or a threshold-based nonlinear response, it can be because of multiple reasons. It can be just pure threshold based on some constraints that you need to have this much of activity, right? It has nothing to do with interactions per se. It can also be because of interactions, because once you have more than this threshold, you have more recruitment, and because of that, you see a nonlinear response out of that multiplicativity between or among those neurons. So it can be because of different of any of those, and some can be explained in polynomial terms. Some needs to account for interactions per se and how those interactions evolve in time, because not everything happening. There's no timestamp in the brain, right? It's like the way we think about generally in neuroscience, like everything is coordinated. Like I'll come back to it again, uh, but then uh, so yeah, so that's about the nonlinearity. And when it comes to attractors, I personally have not used attractor-based explanations in my work so far. I think attractors are, I personally, and some people might find it offensive, I personally feel that attractors were really good discoveries, and they are very kind of nice explanations, shorthand, but I still think they are like Lego blocks for kids, because uh, they're short in explanations, but they do not have sufficient variability to explain things. And the other thing is that it's hard to believe that there will be an attractor. Like, where is that attractor? So I think when we see some kind of recurrence which follows some kind of variability and some kind of consistency, we are able to have a mathematical equation for that, but or to approximate it using something. But I still doubt that there are attractors actually, and we can use attractors to explain things. That's my intuition so far about attractors.
Yeah, and you keyed into why I like the retractor idea so much, and that's because I really think that the brain is a device of recursion, and
Yeah, yeah,
Offline, I'm going to ask to pick your brain a little bit and discover how I can kind of move beyond
Yeah.
attractors through the idea of
So
recurrence.
attractors resonate very nicely with the intuition of brain states, for instance, right? Yeah, like three brain states, which can be, explained in terms of three different attractors. But the challenge which I feel is that it brings back you to the same encoding thinking because you think that your three different brain states are basically three different attractors. So I feel that because of that toy structure to it, it traps you again at some level. Like it's kind of you go out from one room to the other room, you feel like the other room is big, but it's still a room. So so that's the limitation I personally feel with attractor, and that's the reason I had never been attracted towards attractors, pun intended. And moved more towards non-analytically solvable methods like uh, what we do. Yeah.
Yeah, and I think the toy models are hallmarks of a field that's young. I
That
feel
that's
like
that that's true.
and it's their popularity in neuroscience
Yeah.
is pretty high right now. Usually you'll find out that these models do very well to explain the specific phenomenon that they're interested in that moment, but their ability to extrapolate outside of that is very limited. And so and this is perhaps like just part of the growing pains of our field in which
Yeah.
it really is a moment in neuroscience where it's time to start drawing in people from statistical mechanics, engineering, and physics in order to start pulling in those perspectives to make progress towards a more statistical mechanic vantage point.
Right. No, I actually am pretty optimistic about neuroscience. I mean, as much cynical I sometimes sound about a lot of things, I think it's a fascinating field and we have discovered a lot. My only fear is that, especially with the funding scenario and what happens to the Brain Project and things like that, if we overpromise and don't address our assumptions, we lose the trust and the resources to actually continue the profession and the exploration before we actually be able to hit, or understand consciousness or understand the brain and in the way we want to understand. I think that's my biggest fear right now as a for the at the meta level.
I we're on the same page there. I had a journal club maybe about with my wife and collaborator, Dr. Sarah Burke. And in this, it was almost a book club. And we read the book with graduate students, and it was called Science Fictions by Stuart Ritchie. And he discusses the he discusses multiple issues. Among them are the difficulty and like the nature of publishing in a high tier journal and what that means in terms of boutique publications. He talks about the challenges of uh, publishing a failure to replicate story, but he also discusses the dangers of science as an industry that overpromises.
Yeah.
And and in the United States, a lot of my funding comes from taxpayers. And and perhaps you're keying into this with the Brain Initiative and that the budget keeps getting reduced. And that if we fail to make progress on the promises that the funding agencies were designed to solve, then it's going to start to erode both trust among politicians and the general public. And I remember a commercial a few years back here. It was by the Alzheimer's Association, and it was a little girl, and she said, "Sometime in my like somebody during my lifetime is going to be the first patient cured of Alzheimer's disease." And I thought to myself, that's a bold claim. Like
Hmm.
the girl was 7, and I was like, best case, she lives to 107.
Hmm.
So
Yep.
sometime in the next 100 years, we have the solution to Alzheimer's disease. And I thought to myself, it's a bold claim because I'm not sure what causes Alzheimer's disease. And if
Yeah.
we don't understand the etiology of the disorder, what's your target? What's the
Right.
target that you're going to design a therapeutic intervention to attack? Because after that, we
Yeah.
mainly really have it's palliative care or offering some sort of
See,
and
yeah.
I asked my students, I was like, why do you think that they were doing this? Is it to drum up excitement, enthusiasm? And our best guess is that it's kind of like the coach's conversation with his players, trying to get them excited for the big game. So people contribute money to the Alzheimer's Association, and then somebody's going to have that breakthrough idea that actually really spins it. But between the bench, the laboratory bench and the bedside, there exists this big valley of death that require and that's where the real work needs to begin. Is somebody needs to carry that work from the bench through the valley where a lot of
Yeah.
people die to the bedside. And unfortunately, this kind of goes back to what you and I were talking about. Right now, the scientific endeavor is more interested in technological feats of strength rather than novel philosophical ideas about how the brain actually works.
So this brings me to a couple of questions actually related. So one of the things is that we know the Manhattan Project, right? At that time, US wanted to build nuclear bomb. It got like bunch of best scientists together, from the US and Europe, put them under, in Los Alamos, and like, here you are, here's the money, unlimited supply of food, beer, whatever you need. Okay. And then we just need a bomb. You have 5 years, okay, something like that. So let me propose you, like, you have like $10 billion, $10 billion, no questions asked, no bureaucracy, because we know how much bureaucracy we deal with. Like, so if I have to ask people to walk for like 5 minutes in a room, I have to go through months of permission, right? And the same person can go to the gym in the evening and destroy their, like, whatever, eat a number of like 5 kgs of protein a day, and there's no regulations of that, right? So they don't have to deal with any of that bureaucracy. You don't need to write papers or publish. You have unlimited funding. You can select the team of like 50 scientists. Do you think that kind of model will work for these big problems or not? Or were we dealing with something else at that time when it comes to nuclear bomb, and understanding human physiology or neuroscience is a very different ball game?
Phenomenal question. It, I'm going to give you two answers, and I don't like either of them.
Yeah.
One of my favorite subreddits is one called Confidently Incorrect. And usually it denotes that in situations where there's not much known about the answer,
Yeah.
the loudest, most confident voice takes a hold
Hmm.
and leads the people. But
That's
more
true.
often than not, they're incorrect.
Yeah.
Because if you had any sort of reverence for taking the helm,
Yeah.
like if you understood the scope of the problem, you'd be like, I don't know if I want to I'm not confident enough to say anything here.
Hmm.
So the smart people fall to the middle, and then the not smart people fall to the distribution on the tails.
So we run the risk of, some kind of old dogs taking over the project and bring the people and kind of going towards a disaster with this kind of project, right?
Yeah,
It's a big
and
risk.
you and it's funny because like I felt like that's what Max Planck was saying when he says science progresses one
Right.
funeral at a time. Is because you need the loud, confident, incorrect guys to like die
Yeah.
before I, so I I worry that if we had our Manhattan moment
Yeah.
for neuroscientists, the problem that we're trying to solve is so ill-defined from the word go
Yes.
that
Okay.
we wouldn't even know what we want to solve.
So which is a very nice, point you nailed down here, because with the atomic bomb, we knew the basics, and they had a proper vision in mind that this exactly what we need at the end, and this is how to go, right? There were some bottlenecks to overcome, but the aim as well as the premise was well defined. In this
Mhm.
case, we do not have the aim and the premise, right? Both not well defined. But then the idea that small labs of young assistant professors. So first of all, apologize if I did not address you as an associate professor, because you
Of
just you got
course.
tenure and you're an associate now.
I got
Uh,
very lucky. It was like, I have
yeah,
really great peers.
right. So no, it's a good feat. And then and you would have dealt with these challenges which I'm dealing myself. So you are in the prime in your early 30s, when you have trained, you have the most amount of energy, and you want to make a dent in the universe, right? You want to spend as much time doing research and everything. So you want to invest your intellectual labor into actual research, right? Like intellectually stimulating stuff. But at the same time, the system overburdens you. So for instance, most of our time goes in writing grants. To an
Mhm.
extent now that grant writing has become like when you go to LinkedIn, like rarely I see some amazing finding. All I see is congratulations based on, oh, I got the funding. Well, funding is a means to science. Funding is not science, right?
Mhm.
Right. So we have suddenly become in a celebratory culture where we celebrate fundings rather than celebrating findings, right? Like very
Mhm.
little difference between finding and funding. It's a difference of I and you, one vowel change. But it completely changes the culture of science, right? And we have seen this in the last few decades. So do you think that a small lab setup of one PI with a few, with like a small startup grant, even you're talking about 500,000 or a million, is still very small compared to how much it takes to do something? And most of your time going into management and applicate like permissions, grants, which are highly bureaucratic. A simple grant can be like 200 pages, like for like a couple of $100,000. And then with a acceptance rate of 5 to 10%, on an average, one person means is spending time to write 10 grants at least a year if the rate of acceptance is 5 to 10%. So when you look at how much resources we are burning writing grants and what are the hurdles we have to face during our prime time, and then most senior PIs move towards management completely, and the new postdocs are basically working. We have shifted all the scientific labor to the most unqualified training people in the training modes, right? Postdocs and PhDs. Do you think that model will be able to find a solution to this?
Well, it's funny.
Uh,
So
on the other
that's
extreme.
why that's my second pessimistic take on the Manhattan plan that you and I were discussing. In that, so we get 50 people from the PhD grad student level all the way up to the old dogs,
Yeah,
and we have such a culture that celebrates individualism and the accomplishments of a single person
yeah.
that I don't know if we could all work together. And I hope that we would be able to all work together and put our names aside for a singular accomplishment. But as you note, there are challenges in the culture contemporarily that disincentivize me not taking last author or you not taking last author in a publication because it because and I almost think that I'm not sure if I put this on the grants. I think the grants are a component of this, but it's a publisher perish environment for better or worse. For the reason that to get tenure, you need to put together a packet, and that packet needs to have a certain number of publications a year. And you're going to get sent to a board of people who are going to review your packet, perhaps somebody in the biology department, or maybe somebody in dentistry who understands the nature of your research, but also somebody from the art department or the history or English department. And they don't have the metrics to understand what is a good publication record in statistical mechanics. And all they have is the number. And so academics, being type A people, classic overachievers, stop necessarily doing science, but turn their lab into a publication factory. And it's striving for optimizing not for the best scientific environment, but optimizing for an environment that publishes in the most boutique journals. And that's
Uh,
my cynical perspective.
yeah. No,
Uh,
that's true at the level of, of the reward mechanisms. But even at the level of like, let's say that you are allowed to publish less, right? And let's say you're allowed to publish, wherever you want. Like your tenure committee is like, let's say, gives you freedom, right? And you know that. Even then, do you think it's possible? Because you're like just the grant writing pressure. I mean, how much time it takes away for the grants? I think the whole grant structure is also not optimal. And I mean, it might be a big mouth thing because I'm not very successful with grants so far. But I think it's kind of a suboptimal for solving bigger issues because we can always write like a small project and excel in writing that small draft. And that's what we learned because we are, as you said, we are type A people. So we can excel, if we want to do it in grant writing. But is that scientific excellence?
yeah, I what I have to say, I think it's better than it was a long time ago. What is it like if you had to find a rich benefactor, like in the
That
1700s?
that's very true. It's like especially for like some people, I mean, yeah, it's much better than before. Of course, yes.
And I know it's better here than in some other countries. I know
Yeah,
in New Zealand you would get a very small
yeah,
grant, and you, in a way, there's an argument to be said that given a smaller budget, if you're still interested in the question, you'd have to be more clever in your scientific approach, and which would actually require some heftier forethought about your scientific premises prior to like. So in a way, I'd almost argue that reducing the budget has a
okay,
bit
I
of an
see, I see.
opportunity associated. However, I would agree with you. It's challenging because if I publish 5 papers in behavioral brain research, really good journal,
Yeah,
and I submit a grant and I'm going up against somebody who only publishes in Neuron, Cell, and Nature,
here you go.
who are they going to find? They're not, and it's
Of course.
and so this was also discussed in the Stuart Ritchie book, in which laboratories that have cracked the code in publishing in boutique journals
Yeah.
have trainees that will also publish in boutique journals.
Yeah, so
And
there was a paper in I think there was a famous paper I think in one of the boutique journals themselves. Boutique journals are the ones who talk about these things the most, by the way. So it was a paper where it shows that if you are chaperoned by your PI or by a senior postdoc into one of those journals, the likely that you will publish in those journals is very high compared to those who have not published in those journals during their PhDs or postdocs.
mhm.
Yeah,
and and that creates a bias for, so it ends up being that the people who publish boutique are more likely to get the funding.
yeah,
And then there's an associated study. It was by Arturo Casadeville. I can send you the citation if you like afterwards, in which he said after accounting for total number of eyes on the papers,
yeah,
a finding in a boutique journal is more likely to be incorrect than one that's actually published in a low. And it sort of makes sense because general concerns over methodology or just in proprietary, I'm not going to falsify my data if I'm publishing in a mediocre journal, because
right,
what's the point?
right,
The data stands on its own, and there's no need to
right.
overshine the data. However, there are circumstances in which fabrication or scientific misconduct occurs in publication in high tiers. I'm not saying that that's the case for all high tier publications or even in the ones that are
Yeah.
incorrect. Sometimes it just ends up being that the p-value ended up being less than 0.05, and that was the 1 out of 20 instances where it would have been.
Yeah.
But over, so it ends up being just like the random chance where it's not a replicable result. But
Also,
I,
2,500 words is a little too small to convey something substantial in general.
especially in the era when everything is online,
Yeah, exactly.
I mean, there's no, why limit it when when the digital space is almost effectively free.
Right.
No, I don't remember the last time I printed out an article on paper anymore. It's just easier for me to annotate and maintain a library online.
Yeah, I mean, so the good thing is that despite all these things, people who are driven, like working, like we work continuously, right? As like scientists, like I think we have insane amount of working hours, compared to a 9 to 5 job, because of the self-motivation. But at the same time, I think there has to be, okay, here's the thing. So just like we were talking about scale, right? Going from a monosynapse to the whole, nervous system working. The nervous system is trying to work to solve a different problem. And the neuron has no idea of that problem, right? Likewise, we can draw an analogy in for these bigger things, an individual lab cannot even have an idea of where the solution is, right? But the whole system has to solve that problem, right? That's why public has funded us. But the challenge is that, and going back to the evolution, multicellular life was possible only when multicellular cells were able to live together. If each and every cell is trying to live for themselves and killing each other, you cannot have a multicellular life possible, right? And sustainable. And that's a problem with cancer. For instance, cancer cell basically kills its host, right? So there was a big challenge which unicellular life, when it scaled to multicellularity, had to overcome. something which I don't know, maybe evolutionary biologists know it better. Something happened where multicellular life was able to was possible, and that was the existence of all of those things together. And somehow, some way, there was some kind of coordination in that multicellular organisms, that there was some kind of awareness, implicit awareness that the whole system has to work together to be able to survive. Right. Now what exactly is that element or ingredient? I don't know. I think that's what we need, in science, for neuroscience to survive, because we cannot keep on writing articles on encoding and survive individually, because the whole field will die and it won't translate.
Yeah, you have a dangerous thesis that you're working on. The academic system. So this, correct me if I'm wrong. I don't think you're incorrect
Yeah.
either. The academic system is optimized for something other than science.
See, I mean, frankly
Because
speaking,
given this, it evolved for something
yeah,
other than science, given the selective external pressures placed on the level of the individuals. The
right.
system actually ended up optimizing not for science integrity or scientific fact,
Yeah.
but it actually started optimizing for promise and
See,
prestige.
I'll be a little daring here. I mean, I work in a university system, and I mean, I think universities are the best places on earth to work, and they have amazing value. But at the same time, when people ask me like, what do universities do, right? So for instance, I sometimes joke that, universities have two primary businesses. One is real estate, because they own most of the cities where they are,
Yeah.
whichever country you go to, regardless. And the second is endowment. Okay, so universities are into stock market and into real estate. Those are the primary business of the universities.
Mhm.
Education is an epiphenomena. Okay, just like neural firing pattern. I tend to joke sometimes, but you're right, because the incentives for the university, the incentives for the department, the incentive for yourself, for PhDs are all kind of misaligned from the production of information and knowledge to a lot of different aspects, which was not the case with those people who had patrons, supporting their science. But at the same time, I don't want to go to the patron model where I have to find patrons and only then I'm able to do science. And if I cannot find, because of some social bias, out of any demographic group, I cannot do science. So I love the
Mhm.
democratic aspect of modern science, but at the same time, I think we still have not discovered a proper structure which aligns the incentives for us for greater good.
I think you're right. I mean, other than Oppenheimer and a few other characters, there were hundreds of physicists who worked on the Manhattan Project, and we don't know
Yeah,
their names.
exactly.
And I kind of think like to flip everything, maybe a system that's optimized towards actual scientific outcomes would be a group of it, I would actually say, and I think it would be best handled by a group of postdocs and grad students who aren't encumbered by the idea of their professors that taught them 20 years before, but
Hmm.
rather more open to consider more heretical perspective, even if just for instance, consider the alternative. And especially for if their intention was for the sheer curiosity of the scientific question rather than having their name on a paper. Like
Right. Right.
outcome driven, not paper driven.
But this is, yeah, I mean, it's so interesting that, when I was applying for my grad school 10 years back or something, things were very different. Now, and it happens to me when I look at applications. Because if you are now applying for a good graduate school, most of the people who are applying already have worked in some lab for 2 to 3 years. So you have undergraduates who have 3 publications. So you will have
Mhm.
applications from undergraduates who have 5 publications now, right?
Yeah.
So other undergraduates have to cope up, because when you see a publication, you already know a student has worked on a research project. So it's kind of a Red Queen hypothesis here, that the bars for every level is going up and up every day. You know, now one can argue that it's just like Olympics, because the Olympic winners in like 50 years back cannot even compete with like the last one currently, with the advancement of technology, how much technological aids they use, what kind of training they get, the dietitians, the nutritionist, and things like that. And likewise, you as scientists, we are giving you Mendeley and Overleaf and LaTeX and this and that, the tools, and you don't need to submit letters by post and put stamps on your article. So we are enriching you so much for your work that even then it's kind of legit to increase the bar because you are exposed to now those technologies and you have all that support system with you, right? So it's like, I mean, there's no looking
I
back in terms of
that's a very
conservation.
optimistic. That's an optimistic take to me that the kids are evolving so rapidly that they're outpacing us 10 years ago. I'd like to think that I would be competitive 10 years ago, but that being said, like you're right. Like I came out with like a second author paper and an acknowledgement on another,
Hmm.
and I had a 3.25 coming out of undergrad. I don't know. I don't know if I'd be competitive for grad school today. And I was a lab technician for a year and then I got
Hmm.
in. And yet grad school is where I really found my stride. And so I'm not sure. It's optimistic to think that the kids are accelerating at such a rapid pace that we should come to expect that an undergraduate applying to a competitive grad program should have 3 to 5 publications. But I think I guess the cynic in me makes me think that that student is also type A, and that student understands the metrics that they need to acquire, and it's by hook or by crook they're going to get what they need, and they're going to get those 3 or 4 papers, and they're going to make sure they they're going to be very rigid and regimented about how they achieve and knock off
Yeah.
those standards.
Yeah,
I I,
which,
I I
yeah,
worry that we're contributing to a deluge of literature that only an AI would be able to sift through eventually.
right. Which I actually feel, when I attend grant writing workshops, which I like because they have improved my writing and everything. But at the same time, so far I've never received an input on actually on the content and on the project. It's mostly the wordplay. It's like just
Mhm.
wordplay and wordplay and wordplay. And then of course, I'm getting better at it and yeah, I mean everyone who attends grant writing workshop does better at it, and it's good. But the thing is that it completely becomes a own exercise in itself, devoid of, the scientific thing. So it's you wonder sometimes, and you get into the existential vacuums, like why exactly am I doing science?
Yeah, writing a grant, it's its own. It's an elevated elevator pitch, right?
Yeah.
You're sell the science. You're try to get somebody who doesn't think about your problem excited about your problem.
And the most the funniest part of that is some of the same people who have told me that grant you need to love writing grants because, and I do enjoy those, because then you can polish your ideas and like think like a grantsman and things like that. The same folks will later tell you that what, you should apply for grants based on what they want to see, and then you do with the money what you want to do. Okay, and that's what all successful scientists do. So the kind of cognitive dissonance around grants is like just phenomenal.
It's a challenging game, and it's
Yeah,
always about I've never had much luck in applying for funding
yeah.
that that was outside of my wheelhouse.
Hmm.
And I almost think beware of the money that you don't want. Beware of being funded for the project that you don't want to do.
Oh, I've seen disasters, literally. I mean,
Yeah,
you
right.
should be very. I have seen like projects gone astray. Like almost nothing happened out of like $500,000 grant. Yes.
So I remember the dark days where we didn't have much
Yeah.
funding and I was applying for almost anything.
Yeah.
And sometimes when a rejection letter came through, I have to admit I felt relief. Like I was
Hmm.
like, whew, like
Yeah.
don't
Yeah. Yeah.
like okay, now we don't have to worry about recording the spinal cord during and freely behaving. Like I good.
Right. Right. Right.
Um, because I perhaps overpromised there trying to get the science done. And it's more about finding a balance between I've had the best success optimizing my interests to a relatable problem.
Hmm.
For instance, my collaborator, Dr. Sarah Burke, has a strong interest in aging, and I have an interest in aging as well. And of course, the manner in which activity is distributed in neural networks and whether or not it's an energy turbulent cascade it fits in on that picture. And I can start talking about how activity propagates from the entorhinal cortex of an age animal into the hippocampus. And it probably is related to memory. And I don't need to fight my philosophical battles on the grant page. I can fight those battles in the manuscripts.
Right, right.
And I pick and choose about the platform that I present it, and allow the reviewer to interpret it in
Yeah,
their way, and hope I can provide a database that, if nobody liked the answers I provided in my manuscript, well, open data, I'll share it with everybody. You
hmm,
analyze it, and hopefully you can take away more or better conclusions.
right. And that's a good part with the open, data kind of environment where we are not tied to one interpretation, and the funding is, and the resources are justified and open to other interpretations. When somebody reanalyzes those data. That's very true.
I'm in love with it. I remember when it was first coming out that there was conversations of data parasites
Yeah,
popping up. I would actually,
I was one of those. Yeah,
yeah, I was one of those too, right? Like there was times where I was starving for data, and I had an idea and I could use somebody else's database and analyze it. And so I became sort of a data parasite from time to time. That being said, I also feel like it's a good repository in order that, should anybody have make a bold claim and share the data, then it's up to us as a community to test the veracity of that data and make sure it wasn't algorithmic dependent. It wasn't something related to the nature of the toolbox they
I mean,
applied.
I don't consider data. I kind of take offense in the word data parasite because it's not a limited resource which somebody is reducing somebody else's ability. It's like telling that all the photographers are nothing but reproducing like this nice scene. I mean, photographers are not taking away anybody's anything, right? And if they are able to
Mhm.
convey that and find meaning in multiple ways with different lights and different, perspectives, it kind of enriches that place rather than actually they're being parasitic about on that landscape. So I personally don't like that word, although it's common. Yeah,
I feel like it exists, and I guess what's funny is I've had 5 years with a database,
yeah,
and it was like golden database for me, and my students were doing great with it, and they were making all these discoveries, and then I released it into the wild, and somebody found like an awesome discovery in it. I'd be like, ooh, those data parasites, they got me.
yeah.
And it's just kind of like if I were to do that to somebody else, I imagine it's like sour grapes. I have sour grapes. I'm upset that somebody else had high success and asked to really. And it's kind of like I always think to myself, that's the wrong mentality. Science really is a field where a high tide rises all boats. And if they made a cool discovery off of it, and we made cool discoveries off of it, then we're all enriched here.
Of
And
course.
I need to drop this individualistic mentality of like it this discovery didn't come at a loss to me. This discovery came at a boon to the field, and we're all enriched for it.
I mean, if I have an idea and somebody wants to execute it, I mean, go ahead, because then it's kind of it kind of takes away the load, and now I can think of an even deeper idea. I mean, because there's no depth. There's I mean, it's like bottomless. Science is bottomless, right? So if you want to be happy with like low hanging fruits, and just numbers, then it's okay. Otherwise, take away the idea. I'll have something better to dig for.
Well, exactly, right. I mean, that's the true test. The true medal of a scientist is, you take away their current research program, can they come up with another research program? And
That's very true. Yeah.
because it's I guess I was an undergraduate in a research methods class where the person who was teaching the class said, like, I'll tell you right away, like, what makes a good scientist is like, I was walking down the street one day with my friend.
Hmm.
My friend looked over, and we're in Pittsburgh, and there was like this old coal trough that they would dump off the coal into the, and his friend wasn't from Pittsburgh, and his friend's like, what is that thing? Tell me about it. And he's like, he's like, I can tell you right there, my friend was destined to be a scientist, because he'll stop in his general life and ask about a phenomenon he doesn't understand
Hmm.
and seek to inquire more information. And he'll continue to prod and ask about different ways it operates, and in order to figure it out. And he says it's sort of an insatiable curiosity.
Right.
And he's like, and it's like, if you were going to never study your thing, he's like, or your field never existed, he's like, you probably would still end up being a scientist studying something else that interests you.
Mm-hmm.
It's innate curiosity that should be the drive, and not
Right.
a specific puzzle or problem.
So bringing back this perspective to neuroscience, how much do you think is because so for instance, it's very hard to do neuroscience or any deep science right now sitting like a philosopher, right? I mean, you can do philosophy, but at the same time, you need to measure things. You need to be able to see inside the body and manipulate it, right? And it's not a low-hanging fruit anymore, right? The technologies are expensive, the computational tools are expensive, things are expensive. Given that expense, we need to have a structure to it. For instance, we cannot have like a public library of like fMRI, like a public MRI place, like anybody can come, lie down and get the data. It has to have structure, it has to have rules, regulations, a number of constraints. Do, where do you think like how does that restricts our thinking in terms of like computational models or like for instance what a volt signal means, but we still do a lot of fMRI. We overinterpret fMRI, for instance, and what has it allowed us to do in the structured space? Or there's some, can we shift the sweet spot somewhere else, a little bit to have more, to think about the brain or the body like more from the first-hand principles rather than uh,
So
applying the data.
I if I was going to reformulate your question, are you asking about the divide that we can start to draw between philosophy of neuroscience and then the things we can actually measure?
You can say that, yes.
I remember there was a debate. My advisor would always, my thesis advisor, Bruce McNaught, was always hesitant to use the word consciousness.
Yeah, I mean, I
Because
myself am, yes.
yeah, and he's like, I can stick an electrode in the rat's brain and I can record signals that say so and so. And
Yeah,
but he's like, I don't know what the neurophysiological signature of consciousness is.
right.
And I was thinking, well, that's unique because that's a problem that's very much dealt with in philosophy departments all the time. What defines how do you know you're conscious? Well, you think
You
that
talk about consciousness, you become the most
yeah,
popular professor among the undergraduate students. Yeah.
exactly. And
Yeah.
so I may be an outlier among my peers, but I would guess that there are people who come around this way of thinking, in which I think it's time that neuroscience starts questioning the premise of the ideas and the problems we wish to tackle, and actually come from it from an evolutionary point of view. What
Hmm.
did the brain evolve to do? And under that guise, begin to ask how it does that. So a very simple idea is that the brain has to sense the environment in a way that allows it to make a prediction and adapts. And so a good trivial example is a rock is moving towards your head.
Hmm.
And your prediction is it's going to hit my head, and your movement is out of the way.
Yeah.
And what that affords you is survival.
So,
Right?
so, but then you are moving closer to the ecopsych, theories of Gibson and Gibsonian ideas of the, and it comes with its own baggage, right?
Well, I think funny enough, it moves me towards. I probably got this perspective from Donald Hebb and Carl Ashley,
Yeah.
in which they both define the most complex problem of the nervous system is that of stimulus equivalence.
Hmm.
The ability of the brain to identify an object as maintaining its own identity despite changing characteristics over time.
Hmm.
So my dad still recognizes me as me,
Yeah.
despite at one time I was believe it or not, I was an adorable child.
Right.
And then I grew up into this. And my dad still views me as the same person. And so he is able to maintain the same
Yes.
perspective. So
Yes.
despite all the stimulus about me changing,
Yeah.
he perceives, they said that's the hardest problem in all neuroscience, and neuroscientists aren't paying attention to that.
Yeah.
And other instances of it are like I could hold up a playing card and I could like change the way it falls on your retina,
Right.
and yet you would be like, oh, that's still the ace of spades. I can hold it all the way. And even the manner in which the activity enters your nervous system, falling on a different spot of your retina, activating a different group of neurons, cascading to a different group of neurons in the thalamus,
Yes, it's still the same.
still the same. And I think every organism across evolution has to, at least at first, maintain an equivalence with something in their environment
Yeah.
in order to know if it changes and if they need to adapt.
Right. Right.
I don't know any laboratory that studies that today.
You're right. I mean, what if like your one kid is not changing, the other is changing, sudden discrepancy, you know? I mean, I'm just trying to think of like of a lab experiment where, you have constancy, but you do not have like kind of discrepancy in equivalence, among multiple stimulus or multiple objects. But yeah, you're right. You're right. It's a big thing.
And then it's unique because
Yeah.
we have things like cross-modal object representation where
Hmm.
your eyes could be closed.
Yeah.
I'd be like, matter, close your eyes, and I would put glasses in your hand, and
Yeah.
you would hold it, and I would be like, what color are the glasses? What color are the lenses? You
See,
would you would have very good guesses.
very good guess. I think EcoSci kind of touched upon it a little bit. So, for instance, in one of the experimental paradigm where they drop the objects and ask people to listen to the sound, and they asked them to wield the objects in their hand. In both cases, they found when the perception had equivalence, it was based on the moment of inertia, and that same moment of inertia, which was people were, kind of perceiving while wielding, it was the same moment of inertia was producing certain kind of sound structure when it was falling, which was contributing to the equivalent. So I think uh, the ecopsych had this vision in mind when when it started, but of course, things have been stagnant for some time.
So this is the sixth vital motion.
This is the experiments done by Michael Turvey and colleagues at University of
Okay.
Connecticut. Yeah,
I think it really points to that while we're tempted to break things down into very specific sensory modalities,
yeah,
the brain most likely evolved in a way that induces a sort of a soft degree of synesthesia where we are able to equate things, perhaps unknowingly, perhaps a little bit more, some of us more cognizant than others, in which we are able to hear the inertial.
yeah.
We understand what inertia and what the sound of it hitting sounds like, and then we understand what it feels like. And so in a way, we can draw equivalents across modalities to determine that they are make a really good guess at the same.
I agree with you completely with the problem. The challenge is that, so when you look at traditional sensory motor neuroscience, for instance, it deals with sensory motor integration of multimodal, input. uh, our models are still based on signal processing, the way we think of the computational signal processing. For instance, in the lab, we collect data from eye tracker or EMG, and we have like the clock of the computer. So we have each signal coming based on the clock, and we sample, right? And finally, we have a synchronized signal. We can sample at 200 hertz or like 1000 hertz. We can still kind of coordinate them, right? And then you can have a compiler which coordinates to the two and things like that. As we discussed, to begin with in this session, we have so much of delays and change in properties across neurons and things like that. When we are talking about multimodal integration inside the body, there's no single kind of a clock against which we can, match the signals or match neural activity. We do not have like a time course in that sense. We do not also have like a what do you call it, like an even sampling. Okay,
Mm-hmm.
it's the sampling itself is uneven and chaotic, you can say, right? Not just the signal, but the sampling itself is because sample is based on a perception or an action, and that action itself is not like discrete, right? So there are challenges at multiple levels uh, to infer from the brain exactly how that whole thing is happening. So what are the methods which are best suited for that? Apparently, linear signal processing is not. So
I got caught up in what you said about unequal sampling because I think that's fascinating, and especially right now, some of the folks in the field are very much interested in they think that there's neurons of the hippocampus that encode place and other neurons that encode time. And I'm kind of agnostic to all of that because I feel like those are correlations.
yeah,
But when I think about our perception of time, I remember busy days at work seem to fly by, and the slow days of work, man,
yeah.
they really drag on. And so I really do. You're right. I have an unequal sampling of my own perception.
I mean, you have a loved one, in a hospital. I mean, time just doesn't pass us by.
Yeah, man.
So
And and it's funny. So I always thought that the my perception of time changing
yeah,
was dictated by how fast the stimuli changed in my environment or even in my own head. If I'm thinking about a problem really intensely, I can lose track of time.
hmm,
If things in my environment are changing around me really quickly, or I'm watching a movie, my perception of time, I feel the time flow.
yeah,
If you show me a picture and ask me if time's changing, I would say no, it's a static image. But
hmm.
unknowingly, what I've done is I've also put myself in a position where my own time doesn't change as fast
I mean,
because
that's
the
exactly
sim
the reason we wherever we are, like we have 2 minutes, on a bus stand or wherever, we just the first thing we do is like take our smartphone because we are
yeah.
trying to create the stimulus. So that's the reason why we're doing
So
that.
it's funny,
Yeah,
the things in our spatial environment
yeah,
dictate our perception of time,
yeah.
but our perception of time it's a bit of reciprocity in which space and time are actually probably dealt with in an equivalent manner in the brain.
In equivalent manner, yes. And I think we still need to understand that. I think our understanding of that is as it's not even in infancy when it comes to the brain.
I think that I don't think this is my derivation. If I had to attribute to anybody, it would be probably Yuri Buzaki said it. Our movement is a manner of meters per second, how much it changes distance over time. Our vestibular system is distance over time or
Yeah.
acceleration. And our optic flow is a sort of perception of distance over time.
Yes.
So even at our first sensory inputs, space and time are dealt with in an equivalent sort of
R-
manner.
Right.
And so everything that follows, it'd be strange for the nervous, everything within our brain. It'd be strange to actually for the brain to try to split and parcel those into this is space exclusive and this is time exclusive.
Right.
So
And but our measuring devices, almost every device, has a clear splitting between space and time.
yeah, but the toll of the investigator seems to constrain the questions that we are capable of asking.
Okay.
Right?
Okay. So this is a very fascinating question because now I think I we need to put a deeper thought whether tools which split space and time actually have the capacity. Philosophically, there might be some theorem to prove or disprove to investigate a system which does not split space and time.
So,
Here,
are you looking for a tool or an experiment that would actually try to start driving a wedge between the two?
I'm not sure. I mean, I'm just talking off my head, here. Uh, but it goes into the idea that, whether our probes are actually sensitive enough to understand, at least in this case, a system which does not split between the two.
Oh, I almost think we need better philosophical ideas about how the brain would even do it, to how the brain even achieves sort of a way of
Yeah.
if I showed you a card and the card didn't change in space, it's hard to see how much time is happening. But you understand that time if you see the card move or displace in space, you understand that time's moving. Uh, the stimulus equivalence problem begins to actually start asking the question of what neurobiological mechanisms are capable of solving it.
Hmm.
And I imagine that if we begin to scratch the surface of that answer, we'll find a similar neurobiological mechanism by which the brain achieves both representations of things in space, as well as understanding passage of time. Because it's all about understanding how fast is that stimulus changing in the environment in order to how fast do I need to react. If it's a slow moving, if a car is approaching me really slowly,
Yeah.
I understand. So, and I'm doing a distance over time calculation. I understand I can get out of the way at my leisure. But if it's coming quick, I better hop.
Right. Right.
And so I think the way in which my brain has like in one mental snapshot, the car is this big, and the next one, the car is right up in my face.
Yeah.
Well, that stimulus changed quite a bit. I gotta hop out of the way.
Hmm.
And so I think if we understand the nature by which the neural mechanisms of the brain can solve stimulus equivalence, we start keying into how the brain deals with concepts of time, why the time sampling becomes unequal in certain circumstances. Like if you went
Hmm.
into a sensory deprivation tank, I
Yeah.
hear one of two things: the time flies by, or people feel like they were locked in there for 2 weeks.
Right.
And it's either because things in their mind are going so fast that the time flies by,
Hmm.
or the people are so tuned in their external environment and nothing changes, they feel like they've been there forever.
Right. So there's some kind of an equivalence there. Yes. So Andrew, I'm aware that you have to leave soon, but I'll ask you one more, question with a little detailed answer, at least if
Sure,
time permits. Uh,
absolutely.
and uh, and definitely, I mean, I think we have just started scratching, and there's a lot we can, discuss and probe. Eventually, probably meet again. Which is that we have a lot of so when we talk about brain specifically, we talk about waves like alpha waves, beta waves, theta waves, or in general sinusoidal structures. Okay, in our measurements, do we actually have structures in the brain which produce sorry sinusoidally or that kind of strictly oscillatory structure, or is it an artifact of our Fourier transformation algorithms?
Man, you're fascinating question. So the name of the podcast is Beyond Phrenology. And right now we find ourselves in a time, but I just want to point
Sure.
out this wasn't a plan. I didn't ask you to ask this question. It's funny because I was talking about my collaborator Andres Kyle about this issue that's prevalent in my field and his field as well, in which we have a sort of spectral phrenology going on.
Yes. Oh, I
And,
didn't know the word, but it's amazing. Yes, spectral phonology.
yeah, well, so you see the fMRI images, and that's blobology. We have spectral phonology in which like alpha does this, beta does this, and and it even got to a point that it's a very engineering inspired solution in which the brain multiplexes by one slow frequency is transmitting one piece of information and one fast frequency is transmitting something else.
And the thing
And
is that it has such a small bandwidth in the brain,
yeah,
then it's like it doesn't serve the purpose, even if it is working like that.
and it's funny because it I make it clear to my students and the students in my neurophysiology class that first and foremost, what we record when we record the local field potential, 90 to 95% of that is synaptic transmembrane current.
Hmm.
So what you're recording, be it whether or not you want to call it an oscillation or a burst, whatever you want to call it, you're basically recording the aggregate integration of synapses that your electrode can hear from
Right.
that distance. Uh, what is the so then the next question I usually get is so I have an 8 hertz theta oscillation. What does that mean?
But even that 8 hertz oscillation data is coming out of some kind of transformation, right? Because the signal when you
Yeah,
record is not like 8 hertz, right? But the thing is that if you assume an additive model where actually you have sinusoids overlapping with each other, which is basically the Fourier transform, right? Or Fourier theorem, that's where you are getting all the signals out from it.
yeah,
So first is like there's an assumption that it all adds up. And my friend Damien, he says that brain is not a Fourier generator. Okay. And the second assumption is like, yes, if it is 8 hertz, what does it mean?
yeah. So it's a great question. So Gerald Edelman was the one who kind of, and I think Yuri Buzaki as well. It's it's the activity. The 8 hertz is not necessarily only a physiological oscillation. It's also an anatomical oscillation. It's how long it takes for the cortical hippocampal dialogue to actually complete.
Okay.
Or so it's a volley of dialogue between the cortex and hippocampus where they kind of end up propagating activity back and forth to the point that it's kind of like a ring attractor. And
So,
so
so if you are talking about, like, for instance, a more involved process, like in which, for instance, you have more visual stimulus as well as you have memory and things like that. So basically, you increase the loop, in some way that will slow down the frequency. So you have more like lower, smaller frequency responses associated with those behaviors.
we actually
Is
have the
that
flip. So when my rats are really concentrated and running really fast, the theta amplitude picks up and the frequency moves faster.
okay?
Now, however, what I did is I reduced the nervous system to one loop that
Hmm.
communicates at 8 hertz. There's there's loops with it, and this kind of keys in the fractal nature of the nervous system. There's loops within loops. And the smaller loops are kind of like our microcircuit that we're talking about between interneurons and pyramidal cells or interneurons and interneurons.
Hmm.
And because they're a lot closer in proximity, they can have conversations that are a lot faster.
Yeah.
And so that would carry our faster oscillations like gamma.
Hmm.
But because they're smaller in amplitude, they're smaller, they're just fewer numbers, and it's a really local communication. The amount of synaptic activity that contributes to that band
It will
is
reduce. Yeah.
much lower in power. It's like it's at least 1 or 2 orders of magnitude smaller than theta.
Hmm.
So the mistake in my mind of contemporary neuroscience field that could probably be tweaked is there is a sort of Fourier fallacy in which a neuroscientist is going to run the Fourier spectrum and see a peak and key in on that peak specifically and want to understand the meaningful relationship that it is. I always equate this to kind of you take a picture of a tiger in the wild and then you start counting how many orange pixels there were versus number of black pixels. You're literally missing the point by getting too fixated. You have to understand that it's an algorithmic abstraction, but it doesn't tell us anything. It's a transformation of the biological signal.
Hmm.
And that parceling it any further requires a biological premise to carry out the idea.
Yeah.
And in my mind, synapses are unaware if they contribute to 8 hertz, 80, 170. They don't know. And more often than not, they probably contribute to all of them simultaneously.
Right. As well as there's no kind of central mechanism which, like, I'll recruit that synapse.
That's right. That's right. It's a
So
popular, and it really is. It's like it's a cascade of energy that is fractally distributed.
yeah.
So our big loops carry our big high amplitude oscillations, and then you go down a fractal level, and you'll find out that that's usually the next level that carries the next prominent oscillation,
Right.
and you keep until the energy really moves down this sort of fractal anatomy, and that's the manner. But the EEG or LFP and the entire Fourier spectrum, in my mind, is a consequence of a single unitary process of the nervous system, moving energy from one brain region to the next.
Hmm.
And so I perhaps
Yeah.
I find sympathy in what Damien's saying, in that there is a Fourier fallacy that occurs, and a lot of neuroscientists should beware of spectral phrenology.
Yeah. No, that's a very convincing, response you gave. I mean, I often ask this question, like, rarely have I found like such a convincing and, kind of a rational argument, explaining this.
Well, so it's funny. So I tell my students this is my hypothesis, and I challenge, like, this is the hard part of our jobs now. Let's design the scientific test
Yeah.
to prove me wrong.
Yeah,
Let's
exactly. That's experimental design, of course.
because
Yeah.
I can find somebody else's bad hypothesis and prove them wrong all day.
Yeah.
But as we know, Max Planck tells us that I will never convince them, and they're only funerals progress science forward. So instead, my time will be better suited by designing my own experiment to kill my own hypothesis.
Well, in science, the funeral can be biological as well as like, grant wise.
Yes, yeah.
So, so,
That's a
so,
good.
so granting agencies can actually, create funerals if they want.
Yeah, yeah. For better or worse, I mean,
Yeah,
there's a phenomenon called the Zollman effect that if you're on the outs of the popular science networks,
yeah,
you're most likely going to be while you survive the last evolutionary round, your laboratory and your offspring may not survive the next.
uh, okay. Can you
So
explain a little more on it?
sure. So we were
Yeah,
talking about if you came from a laboratory that was producing boutique publications
yeah,
and getting the NIH grants,
yeah,
and then you strike out and get boutique publications and grants.
yeah,
There's another laboratory. They don't publish boutique. They publish really solid
yeah,
scientific findings, but they're not going to set the world on fire.
right.
They're going to have a harder time getting grants.
Yeah,
And because they'll have a harder time getting grants, you're going to have a harder time getting students.
yes,
Because they have a harder time getting students, you're going to have a harder time publishing papers.
yeah,
Harder time getting, and so it creates a sort of
yes,
ecological environment by which it's no longer even publish or perish. It's starting to turn into publish boutique or perish,
yes.
which is giving the boutique journals a stranglehold on the course of science, which brings us back to the dangerous idea of whether or not the academic system is optimized for something other than good science.
So, the thing is that if you can, so you land on a big grant, you have three postdocs, right? Each of them will submit like a one grant each a year, something like that. So the thing is that grants breed grants in the sense that you can invest more time of grants through indirect resources. You can hire grant consultants and things like that. And then it also becomes difficult to publish in journals these days without grants because now more and more journals are turning APC. For instance, like the whole NPJ series in Nature, right? NPJ starts a journal in any field, it becomes the highest impact factor journal. And the traditional, society journal will kind of decay with its impact factor. And then you need money to publish in there.
Mm-hmm.
So it's a cycle which will, I think it will reach a tipping point when we will rethink, how it is actually how it is going.
What
Or
do you imagine? I struggle to envision the event, and I guess perhaps it's a limit of my own imagination.
yeah,
What would be the event or the stimulating thing that would actually cause the tide to turn?
I think it will be economic crisis
Oh, okay.
because I think we are living in a lot of fake inflation. It comes out of our monetary policies and it percolates toward general culture, our morals, and everything. So when you have a granting agency which is giving you like money and like few $1,000s, and now you have organizations coming up with rules like if you have public money, you have to push open source. So what they have done is like instead of asking universities to start archives or themselves starting an archive, like for instance, we have PubMed. We can publish
Mhm.
directly on PubMed, right? Why do we need to publish with like some other journal and then put on PubMed, for instance, right? So that's basically funneling out the money from research to actually and I'm not against journals, right? I mean, everything is making profit.
Mhm.
Scientists are making profit. Our reagent companies are also making profit, right? You have this outrage against journals, which you don't see against GE, for instance. GE make fMRIs, and fMRIs are so expensive. But you will
Mhm.
never see neuroscientists talking against GE, how much profit GE makes, right?
Yeah.
But they will always go against journals because they're easy targets. So I'm not trying to, vilify anyone. I think it's an incentive structure where you are incentivizing. Uh, I mean, I personally don't think about journals anymore because for me, I would rather not format the publication for other journal than I would rather spend the time in exploring and doing more science. So I don't even care about journals. I'll just write the manuscript, send it wherever I know that it will not go through a lot of issues, which I pay the price for because I don't have boutique journals. And I don't like boutique journals myself because boutique journals are not run by scientists. The editors are basically most of the times you can call them like failed scientists, in like I mean, and that's what most of them are, right? So
I
yeah,
yeah, again, like I tell my personnel that I do not publish boutique, and I nor will they ever find me pushing them to publish into boutique journals because one, I find it to be a bit of a cabal, who you
yeah,
know, and if they're going to gatekeep you. I wasn't popular in high school, and I don't imagine I'm going to be more popular today.
I mean, same
So
with me. Yeah.
I wasn't destined to be part of the in crowd, and so
Yeah.
I will I'll continue to I'll support my the membership journals, the institute journals. I'll always support those. I'll always submit to them. The smaller journals will always have a close place in my heart. And the reason why is the same as yours. I don't want to get locked up in revisions for
Yeah.
a year and be asked to run experiments on more animals when I kind of feel like I know the answer to that question. And of course, completing that project made me think of three new questions that I'm more excited about today.
Right. Right.
By the time I write the manuscript, the analysis and the ideas already 9 months behind
Yeah,
me.
exactly. It's like I want to be in the future rather than still, boasting about my past.
Yeah,
And
exactly.
the other thing is student training. For instance, when I was an undergrad, I started publishing when I was an undergrad, and my professor was very promotive of it. And he let me, write my own paper, submit it in a small journal and things like that. So I learned through that process. If I take all the data and just try to publish one, like some big journal, somehow taking all the students' data or something like that, or my collaborators' data, then where is the learning process? Where is the iteration?
Mhm.
Where, it comes at a lot of sacrifice of a lot of souls. So we often see the Nature paper, we don't see how many souls did not get authorship.
Yeah.
We often don't know what has gone into that. So I don't want to be part of that game. So I was initially very much like, oh, I'll publish big, big.
Yeah.
But as you realize, the more you start enjoying the joy of science, the less these things attract you. They trouble
Mhm.
you on the back of the mind because you're a social creature and comparison, this and that. But you don't want to play that game.
Well, I mean, so I guess a good place to end would be with Richard Feynman and the Manhattan Project. He said you may do flashy science and may temporarily get a lot of fame for it, but the thing about science is the truth will eventually out.
Right.
And
That
and so
that's
so
very
like
true.
I have some papers in some low tier journals that actually will probably prove to be true in 20 years. And that's all I tell my students is make sure that you know this will be true in 20 years or do your best.
Say if we are not for like science, then we better make money somewhere else. To be
I
honest, I mean,
know.
with what academia pays you, it's just for science, you know.
Well, with inflation coming, I'll probably buy some gold now and make it rich on gold.
Maybe. I mean, I lost all those, what do you call, like I never bought Bitcoin or anything, so so
Well, well, no worries. If an economic crisis is on the horizon through perhaps inflationary monetary pressures, we can invest in the euro and make a little bit of money. So,
Well, thanks, Andrew. Thanks for coming to Beyond Phrenology, and it was a lovely discussion. And I'll tell you, my honest feeling is that we literally scratched the surface, and there's a lot more common in way we think than we ever imagined.
hey, yeah, I appreciate it. Thank you for having me, and I'm going to look forward to seeing more of your stuff as it comes out. And
Definitely,
if the occasion ever strikes, I get the opportunity to interview you a little bit more.
definitely. As well as we'll see, some collaborative opportunity, for neural data.
Awesome.
Yeah.
Cheers. Thank you so much.
Thanks. Bye, Andrew. Have a great day ahead.